Hi, welcome to our chemistry pop-up lab at the Ars Electronica Festival.
My name is Martin,
I'm Lena.
and today we're going to show you some oscillating reaction and some other stuff in chemistry.
Whoa!
It gets bigger with time.
Yeah. Today we do a lot of dangerous things because our boss isn't here. But to be on the safe side, I will wear gloves. We want to show you chemical patterns by an oscillating reaction called the Lussov-Slabodinsky reaction. And therefore, we need potassium bromate. We add 2 milliliters of malonic acid. And 1 milliliter of potassium bromide. And then you can see something has happened. The bromide and the bromate reacts together with the acid in different steps to bromine, which you can see by the orange color. The bromine reacts with the malonic acid, and then the solution should get colorless again, and until it's finished we will do a different experiment.
So we're going to show you a reaction that's called elephant toothpaste, which some of you may already know. Oh, before that I forgot something. So we're going to prepare another experiment. It's called ample bottle. For that I need some water. And I'll add some glucose to it. So this is just some glucose that you can buy in the supermarket. I need around 8 grams. One of these weighs like 3 grams. So I'll just add 3 of those. 1, 2. And the third one. Oops. And now this has to dissolve, which will also take a while. And because this will take a while, we're going to show you another experiment that's now called elephant toothpaste. For the elephant toothpaste, I need 3 things. The first thing is just some soap that you can use for dishwashing. Then I need a catalyst. As a catalyst, I add potassium iodide. And for the reaction itself, I add some hydrogen peroxide. Now you can see some foam coming. Oh, it's a lot of foam. Oh, it's too much foam. Oh no! Yeah. As you can see, there's a lot of foam here in the hood. I should not try to touch it with my hands, but you can see. Oops! Oh it's hot. You can see foam. The foam is pretty stable. I added some glycerin to the soap so that the foam gets stabler. Yeah, and while I clean up this mess, my colleague may be able to continue with the oscillating reaction.
You can see the solution is almost colorless. It's colorless, actually. Then we can add 2 milliliters of the ferrine solution. It's a red liquid which can change the color when it gets oxidized or reduced. And you see when I add the solution, it gets immediately blue, and we want to see the pattern. We have to pour the liquid into a petri dish, and we will see the solution under the microscope. What are oscillating reactions? In oscillating reactions, there are periodical changes, and at the Belousov-Zhabotinsky reaction, there are 2 different processes. Which process runs depends on the concentration of bromide. In the beginning, when the solution is red, the concentration of bromide is high. In different reaction steps, bromide reacts with different substances and its concentration decreases. Then process B takes over. In this process, the ferrine gets oxidized, so it changes its color to blue. In process B, the concentration of bromide gets through different reactions higher again. And when the concentration is high enough, the ferrine gets reduced again to the red color, and process A takes over again. And you can see these different processes, the periodical changes in the blue circles on the red ground in the solution. You can see there are some bubbles in the solution. This is because in the reaction, carbon dioxide is forming. Start the reaction again by mix the solution.
So now we can continue with the ample bottle. The the glucose is almost completely dissolved. And I can now pour it into a bottle which has sodium hydroxide inside. But first I'm gonna add a dye. The dye is called indigo-camine. And when I add this dye into the solution turns blue. As you can see, the solution turns blue. I have a magnet here. And when I now pour this blue solution into the sodium hydroxide, you will see the solution turning yellow or green. Put the magnet here to don't drop zero. So now we have the bottle full, and you can see the bottle, it looks green. But what's interesting with this bottle is that the color changes with time. What's happening here? We added a color, a dye that's called indigo-camine. Indigo-camine is a dye that changes color with pH and is redox active. So when I put it into the solution with glucose and sodium hydroxide, the glucose reduces the dye, changing its color, which turns then ultimately from green to red, and then after a while the color changes to yellow. The yellow form is then the reduced color of the dye. This takes a while, but you can already see the color change. It turns lighter and lighter. Ampel means traffic light in English. As you can see, you have the colors of the traffic light, bluish, green. Blue is not on the traffic light, but green, red, and yellow. But the really interesting part of the experiment is that you can change the color of the dye back by shaking it, and that I'll demonstrate now. So you see it's yellow, almost yellow, orange, and now if I shake it, you see the color changing back to red, and I shake it faster and harder. You see that will change back to green. Now it's green again. Why is it green again? Green is the oxidized form. What is oxidizing the dye again? It's the oxygen in the air. When I shake the bottle, the oxygen that's in the air inside the bottle goes into the solution and oxidizes the dye again to its green form. But because the glucose and the sodium hydroxide is still inside the bottle, you will see the bottle changing back to red, and then after a while changing back to yellow. And the funny thing about that experiment is that I cannot do it once or twice, I can do it a few times. So you see the bottle is already getting lighter and lighter red. Starting to sweat here, not used to doing so much work. And when I shake it again, you can see the color changing back to green again. Yes. So this is the so-called ample bottle experiment.
Now we want to show you some experiments with liquid nitrogen. It's about -200 degrees cold, and you can see there's a lot of, and this is because the water droplets, the water is getting so cold that it gets liquid and you can see the fog. It is really, really cold, but when I put my finger just for a second into it, it's not feeling cold because the liquid nitrogen evaporates immediately and I cannot feel the -200 degrees on my fingers. But what happens when I put something a little bit longer into the liquid nitrogen? For example, these beautiful flowers. Wait until it's really, really cold. So, you see, it's no more elastic, it's very hard, and when I throw it onto the table, they break. Let's see with the bigger flower. See, it's totally soft, and when I put it into the liquid nitrogen, it gets hard and breaks into a lot of pieces. Sounds like glass a little bit. Okay, then Martin will be very brave and will show you some really dangerous experiment.
Now you saw what happens when you put your finger shortly into the solution. That's what happens when you put something for a longer time into the solution. But the question is now, what happens if I put my finger long into the solution? What will happen? I'll try it out. So I put my finger in. Yeah, I don't feel anything. And after a while, the finger gets colder and colder and colder. And yeah, it starts hurting a little bit. Oh, but when it gets even colder, I can't even feel pain anymore. Yep, I cannot feel my finger anymore. Yep. I can feel a little bit of cold on my hands, but the finger is really cold. So when I now use a hammer, I cannot even feel any pain here. And yeah. So you can see I lost my finger to science, but the good thing is I have sausage fingers and yeah, they grow back. So this was just a sausage. Please don't try this at home. But now we will show you a really dangerous experiment. Something that's prohibited in the lab. You should not do that in the lab. For that, I'm going to take some popcorn and put it into the liquid nitrogen. Oh my, there's still something in. I don't want to have any flowers in my popcorn. That's too late. Okay. I have flowers in my popcorn. So I put in some popcorn into the liquid nitrogen. Your biological teacher is were they toxic or not?
No.
Okay, perfect.
No
Okay, perfect. So now I cool the popcorn down. And now I do something that's not allowed. I'm gonna remove my mask. Mask is removed. Otherwise the next part gets really hard. And now I'm taking out a popcorn and I put it into my mouth. And you can see there's steam coming out of my mouth. The popcorn I'm eating is also called dragon breath popcorn because it's the steam coming out of my mouth. And my nose apparently. So you see, I did something that's prohibited in the lab. Eating. Never ever eat something in the lab. You can eat at home, but not in the lab. Lena, you want some popcorn too?
Yeah, of course. I also removed my mask. Oh my god.
See, there's the camera.
Very tasty. Some more. So Martin, I think we have to go on with our experiments because the people don't want to see us eating.
But they will have to. Because now there comes an even worse experiment. So we will clean up a bit and then we'll show you the last experiment.
So we shake again the solution of the Belousov-Kapodinsky reaction and hope there will be again some patterns. Yeah, you can see the color is changing from blue to violet. To red, and the patterns will come in some seconds.
Correct. Oh my. Come on. So how does the dragon breath popcorn work? Here I have some glass filled with warm water, and now I add some liquid nitrogen to it. And now you will see that it's foaming really strongly. Why is that the case? When you have something, when you have water somewhere, water always evaporates and gets dissolved in the air. When I add liquid nitrogen, the water in the air gets so cold that the air cannot hold the water anymore. This also happens when you heat something up. Normally the heat the steam goes up because you heat something up. In this case, the steam goes down because it's so cold. And how does the Dragon Breath popcorn work? Exactly the same. The liquid nitrogen, there's a little bit of liquid nitrogen in the popcorn, cools the air in my mouth. I have water in my mouth. My mouth is pretty warm, so that's the reason why we see the steam. I can now show you something. I can also take the steam like that and blow it out. But if I inhale it, you won't see any steam because I heat the air back up in my lung, and then you won't see any steam anymore. So now for the last experiment that we'll show you today, that I'm really fond of, is I'm gonna make something to eat again, and this time I'm gonna make ice cream. And now I want to know from Lena. Lena, what ice cream do you want? We have vanilla, strawberry, or Heidelbeere? Blueberry.
I want blueberry.
With vanilla?
Yeah, okay.
Perfect. Then I'm gonna make a blueberry vanilla ice cream. For that, we need blueberry. Gonna add some blueberry yogurt. Hold my hand that you cannot see any that I don't make product placement. Then I'll add the vanilla. Oh, time is running out today. Oh my god. If you've got any questions concerning any of the experiments, you may ask them in the live chat. So vanilla. Then I'll add some milk to make it a little bit more liquid. Because when you cool stuff down, the sugar tastes less. That's because how our tongue works. I'm also gonna add some sugar. If you're sweet tooth, you have to eat a lot. I think Lena and I aren't that. We are sweet enough already. We don't need that much sugar. And then I stir it a bit. So we have everything inside. But this doesn't look like ice cream. What is missing? It's way too warm. What can we use to cool it down? Exactly, liquid nitrogen. So now I just add liquid nitrogen. And I stir it. And you can see the steam again. It gets harder to stir with time because of the cooling down of the liquid. I feel now a little bit of ice forming on top, which is a good sign if I want to make ice. This will work perfectly. Are there any questions, Lena? Nope, perfect. You can see it bubbling. It's not boiling, it's really cold. Gonna need a little bit more liquid nitrogen. Little bit more and then it's finished. Yeah, a pity you cannot see us eat it anymore because the time is running out. But it's almost finished. Yeah, you can see it. The ice looks really good, and I'll taste it. And it tastes really good. So that was it for today. Thank you for watching.
And we will enjoy now our ice cream.
Have a good Sunday. Maybe we'll see each other again before the chemistry god.
Bye.
Bye.